We are doing another Rosen question from chapter 2.1, question 48. That's somewhat similar to question 47. The definition of A sub I is a little different. But we're supposed to find the intersection and union of the sets A from 1 to n. So let's look at what these A's are. There's the collection of sets that's defined as, you'll notice, all of the negative integers. So it's including every single negative integer. And it stops at I. So A sub 1 is all of the negatives 0 and 1. Now A sub 2 will again be all of the negative integers, and then this one stops at 2. A sub 3 will be all of the negative integers, and it will stop at 3. And this pattern repeats for all n's until we get to the set. Again, all negative integers, and then we're going to count up till n, and then the set terminates. So we can write out as many of these as we want, A sub 1, 2, 3, 4, 5, 6, 7, however many you need to sort of sense of what is happening to these A sub i's. So now we want to find the union and intersection of them. So recall what the definition of a union is. A union of sets means that I take each element in every set in the union and I collect them and put them in a new set. And I do not repeat elements. So let's say I have a set 1, 2, and 3, and I union that with a set 2, 3, and 4. The union of these two sets will be a collection of each element without repeating. So 1, 2, 3, and 4. So that's the union of these two sets. So sometimes more formally, we'll say that the union of a set, if there's an element in the union, that means that element is either in, let's say there's two sets, A and B, that if elements in the union, that it's in one set or it's in the other set. So with that definition in mind, let's look at what the union of I equals 1 to n of A sub I is. So this will be the indexed from 1, the union with A sub 2, the union of A sub 3, and it'll union all the way to A sub n. So we're taking everything from 1 to n. Now, let's remember what it means to be in a union. It's a collection of everything in each set without repeating. So I'm going to take everything that's in A sub I. I'm going to take everything that's A sub 2, everything that's in A sub 3, and so on, all the way up to A sub n. I'm going to collect all those elements into a new set, which will be the union. So if we look up here, we see A sub 1 has all of the negatives, negative 1, 0, and 1. A sub 2 has all of the negatives, 0, 1, and 2, and so on. So at the very least, we see we have all of the negative integers from 0 to 1. Now, if I look at A sub 2, well, now I'm going to add 2. If I look at A sub 3, then I'm adding 3 to this list. A sub 4 will add 4, and so on, all the way up until n. So much like in question 48, or 47, sorry, the union of these A sub i's will always be the largest of these sets. In this case, A sub n. So the union of all A sub i's from 1 to n is equal to A sub n. In other words, all of the negative integers, 0, and then we'll start counting from 1, 2, 3, all the way up until we terminate at n, and that will be the union of these sets. So let's look at the intersection. By definition, the intersection is a collection of elements that are shared by the two sets. So if I have the intersection of these two sets, I see that both sets have a 2, so I'm going to collect a 2. Both sets have a 3, so I collect a 3. Both sets do not have 1, so I throw out 1. Both sets do not have 4, so I don't use 4. So the intersection of these two sets is just 2 and 3. So that applies to our case of all of the intersections of A sub I. Which would be the intersection of A sub 1 with A sub 2 with A sub 3 all the way to A sub n. And remember, the definition means that they all have to have these in common. And if we look at our sets up top again, so A sub 1 has all of the negatives 0 and 1. A sub 2 has all of the negatives 0, 1, and 2. But A sub 1 doesn't have 2 in it, so we have to throw 2 out. A sub 3 has 3, but A sub 1 and 2 doesn't have 3, so we have to throw 3 out. So you can see a pattern emerging that each successive set, A sub 4, will have 4, but the previous sets, 1, 2, and 3, will not. So we cannot include it. So what we are actually left with then is all of the negative integers, because each set has the negative integers. Each set has 0, and each set has 1. But that's it. That's all they have in common. So this is equal to A sub 1. Again, with a pattern like this, usually you're going to have the intersection be equal to the smallest set and the union be equal to the largest set, because essentially it's growing on each other or shrinking, depending. So if we recap the intersection and union, so this was part A, the union from I equals 1 to n of A sub I is equal to A sub n. And part B was not the union, the intersection, which was equal to A sub 1. So that's it. That's the intersection and union of these sets and index sets, much like problem 47. This one is very similar. And again, the union is the largest set and the intersection will be the smallest set when we have a discernible pattern that builds upon each set. That's it. Like and subscribe if you can. Appreciate watching. Thank you.